So today we will start from synchronous motor. This problem appeared in GATE 2022 for 2 marks. Okay, so let us see the problem here. This problem is asking us to find the per phase excitation EMF in synchronous motor. Uh, so how to find? First, we will see what are the data given, and before that, we will discuss a bit basics about synchronous machines or equivalent circuit of synchronous machines. So let us start with a basic circuit, what generally any synchronous machine consists. So let us take example for synchronous motor, since problem based on synchronous motor only. In motor, we give some input. That input could be, or generally it is electrical input. After that, there would be some powers would be developed at armature, and this input would be, we can call input power, whatever we are providing, 3 VI. And after this, there would be some losses here as well, here as well. You guys are able to see my screen and able to hear me, right?
Yes.
Okay, fine.
Yes, sir.
Thanks. So at the end, the power of motor would be transferred to the shaft. So this is the end destination of the power flow. And since the power is going into the electrical side and it is or developing at the armature of the motor, some losses would be there. And these losses are related to electrical side. We are moving from electromechanical. So some electrical losses would be there, core loss and copper loss. After that, this developed power would be there. And here, rotational loss. These are mechanical losses and frictional plus windage loss. These losses would be there. Now, let us see in terms of equivalent circuit as well. It is indicated in terms of lumped parameters. VT, terminal voltage.
सर कोई ज्वाइन होना चाहता है सो ज्वाइन नहीं हो
Okay, okay. Actually, I have done this automatic, so people would not find any difficulty in joining. I guess Sage had joined. Okay, so let me continue here. This would be excitation EMF, right? R, RS, or. Now, in motor, current would be fed from the terminal side. So, this would be IA, and here current would enter, and this is the terminal where power is being developed. This is the terminal where power is going into the motor. Losses would appear across this RS, and this is our synchronous reactance. I want to write some KVL equations based on this circuit. So I can write Vt is equal to EF plus IARA plus JIA XS. This is the resistive drop. This is armature or synchronous reactance drop. This is excitation EMF, which is responsible to establish the flux or field inside the machine. And this is input. Now, if I multiply IA on both the sides, so if I apply VT I am writing in terms of phasor because there would be some angle. I forgot to write angle here. Let us take terminal at 0. Then EF would be lagging by some angle delta. And the current across RS or resistance would be same in the phasor of terminal voltage, and it would be XS would be lagging. This would be so overall. If I write in terms of phasor, so let me write in terms of phasor. VT angle 0 is equal to EF angle minus delta. Since EF at lower level, so it is going to uh, when when power is flowing from one end to other end. So uh, delta 1, delta 2. Just give me a minute, guys. Excuse me. Okay, so I will resume here. So if power is flowing from this side to this side, this concept is generally discussed in power system as well, but I will briefly explain. Then delta 1 should be greater than delta 2 to flow the power from terminal 1 to terminal 2. So that is happening here. This angle of terminal voltage should be higher than the angle of excitation EMF. So that's why I am writing like that. If you have any doubt at any point, you can stop me in between. Further, generally IA in lagging terms, so IA would be with power factor phi. Let us take this circuit had power factor phi, then IA would be lagging with angle phi into RA. We will again break it down. Don't worry about phasors. Plus J IA angle minus phi into XS. So this is the KVL equation of motor, and we will break it while we will solve the problem here. So any issue in this equation or circuit? If not, then we will follow the problem what they were asking. So it is given here synchronous reactance of 1 ohm per phase. Means excess of 1 ohm is given here. 400 volt, 50 kVA, 50 hertz, 3 phase, a star connected synchronous motor. Shaft load on the motor is 10 kilowatt. So there is 10 kilowatt of load, means this power is given here. And power factor is leading. So it is a tricky question where power factor is leading here. Now you have to give a special attention to the power factor because the general tendency of us, the students, is to solve by considering lagging power factor. So we will take leading in account. Loss in the motor is 2 kilowatt. So one more catch, they haven't mentioned which loss, mechanical loss, electrical loss, core loss, copper loss, they haven't mentioned. So they just mentioned that total loss in motor is 2 kilowatt. Now loss is also known 2 kilowatt. So what would be the input power? Can anybody tell me? After that, we will solve the per phase excitation EMF. What should be the approach to solve the excitation EMF? So can anybody tell me what would be the input power in this problem?
12.
12, right? Thanks.
Power output plus loss, and power
The
output
shaft
given.
loss power shaft.
That would be the shaft plus loss. Shaft power plus total loss in the machine. Correct. Thanks. So after that, we have found that input power is 12 kilowatt. Now, I was discussing the power formula here. So in network also the basics is always same. Uh, Apparent power, real power, reactive power. The basics will be always same. And I will explain the uh, breakdown of power in real and reactive from one simple this circuit. Based on one simple this circuit, let us see how we can break in power waveform. So apparent power. We in motor generally we deal with input and developed, because after developed there is another level that is based on mechanical. So either that data would be given or that data would be ignored. So we do not have to worry about mechanical domain. So let's take input apparent power, that would be Vt Ia conjugate. So this is the apparent power input. Now after we will solve here, we know or we can calculate the value or parameter of Ia, that would be Vt angle 0 minus Ef angle minus delta divided by Rs plus Jxs, right? Or we can write it as Vt minus Ef angle minus delta divided by mod Zs angle theta. Perfect. Now we will try to model it in terms of VT IA. Since VT will be given always, IA we have to convert in terms of EF or VT. And IA conjugate I can write.
Sir,
Yeah.
brightness of screen is very high, is not visible.
Okay, my screen is not visible.
Yes, sir. It's very
A,
light.
a skin
Shiny.
is visible.
Okay, okay. The pane is not visible. Okay, I will make it more thicker. Thanks. Thanks for pointing out. So can you confirm it now? Is it visible now?
Yes, sir.
Okay,
Now visible.
thanks. So now I am going to calculate IA conjugate. So while doing conjugate, we just have to change the sign of angle. Since it was here minus delta, so I will change it to plus delta. Mod Zs angle minus theta. So this would be the conjugate of IA. IA conjugate we have calculated, Vt was already there. So I will write it now, input apparent power Vt angle 0, Vt angle 0 minus EF angle delta divided by Zs angle minus theta. Now I will club both the this thing and this thing. I will club now. So Vt square divided by mod Zs. Theta would go upside, so it will become plus minus EF Vt by Zs angle theta. So this was the input apparent power. After that,
Delta plus theta.
okay, okay, I missed the delta. Thanks. Uh, delta plus theta. Thanks. Now, to convert it into input power plus input reactive power, what I have to do, I just have to break this complex angles into cosine and sine. So if I will multiply it with cosine, it will become real input power. And if I will multiply it with sine, then it will be reactive input power. So first I will calculate real input power. That would be Vt square divided by Zs cos theta minus EF Vt by Zs cos delta plus theta. Right? So this was very simple. I just come across the apparent basic formula of apparent input power and I reached to this point, and this is the input power of the motor. If I want to calculate input reactive power, I will do the same thing with sine theta minus EFVT by Zs or mod Zs sine delta plus theta. So any issue till this point? Okay. So I assume there are no issue till this point. And anyway, these sessions are recording. We will upload this on YouTube, so you can also find on YouTube as well. So no need to write anything or like that. If you want to write, you can write, but no issue. After that,
Sir, on which YouTube channel will it be available?
okay, for time being, I will upload on my YouTube channel. I will give the link of that YouTube channel. After some time, it will be uploaded on some official NPTEL also. So at the end of
Okay,
the
sir.
session, I will provide the link of the channel.
Okay, sir. Thank you.
Thank you. So we will again go back on the problem. What was there? So input power we had calculated 12 kilowatt. Now power factor is 0.8 leading. Based on that, we will try to calculate the excitation EMF. And the KVL equation of excitation EMF we had also derived. Now we just have to put everything or collect everything at one place. Okay. P input is equal to root 3 VL IA cos phi. I can write it like that. Fine. Any input power to any circuit, you can write. This is another formula of input. This is one, this is another. So these two formula you have to wisely choose that where you want or where you can use. Wherever current is given, you can use, or wherever you need to find the current, you can use this formula, this one. Or wherever you are given with load angle or torque angle, then you need to choose this formula. So you need to be able in discretion of this both formula. Now I will calculate IA here because power factor is given, terminal voltage is given, input power is given. So I will find anybody trying to say anything? IA was 12. IA is equal to P input divided by root 3 VL cos phi. Root 3. How much VL was there? 400 volt into cos phi was 0.8. And this would come out to be, yeah, I guess 21.65 ampere. But I would bring the angle thing also because we are doing these all calculations in AC. So in AC, ma magnitude is always important, but we have to carry the angles also. Since it was zero point 0.8 leading, so I can write it as plus 36.86. Cos 36.86 is zero point 0.8, so I would write it like that. Now we know IA. We are now going to apply in KVL, and that was nothing but VT is equal to EF plus IA. IA is nothing but, okay, I will again put into RA plus JXS. VT was 400 is equal to 400 by root 3. Whenever we will solve this equation, we should try to convert everything is phase value. Otherwise, it would be mismatch. So 400 by root 3 angle 0, EF angle minus delta plus 21.65 angle 36.86 into RA was absence in the problem, I guess. Yeah, with negligible armature resistance, it was written. If I will go back to the problem. So you can see with negligible armature resistance. So this is the general scenario. In most of the gate problems, they generally ignore the armature resistance. So Jxs was given 1 ohm, J1. Now I will rearrange it. EF angle minus delta is equal to 400 by root 3 plus 21.65 angle 36.86. Sorry, minus, because this would go left side, minus 21.65 angle 90 plus 31.26.86. So after solving, since these both are in real, or if you break down, there would be two components. One would be real, one would be imaginary. So this is just the complex problem, complex number problem. So you will get 231 0.
Sir,
This,
excuse me, sir.
yeah, please.
Sir, can you repeat the above step, sir?
Okay, sure. This step,
21.65 is repeated twice, sir. How, sir?
okay. This point you want to explain me again?
Yes, sir.
Okay,
21.65 is repeated twice. Yeah.
okay,
How,
okay,
sir?
okay, fine. So this was
Okay.
the resistive term. Okay, sure. That was my flaw. I assume that resistance is there. Thanks for pointing it out. I will delete. Since resistance is not there, then I proceed like that. If I would have done like that in gate, I would have lost 2 marks. So make sure this kind of mistakes we should not do. Right.
Sir, if it is not given, then we have to assume like zero resistance, sir.
Yeah, in problem it is mentioned that there is negligible armature resistance. So negligible armature resistance means 0. I have
Zero.
written
Oh,
here J1 only. If some
yes, sir.
resistance,
Got it.
finite resistance would be there, I would have taken into account. But
Yes,
it is
sir. Yes,
not
sir.
there, so that's why. Now
Yes, sir. Got it.
231 minus 126.86. So this is real. This will break into two components. One would be real, one would be imaginary. Again, we can arrange it. It would come out to be 244 minus J 17.32 if you solve this complex equation. And the magnitude of phase voltage, you just have to take the square root of 244 square plus 17.32 square, and you will obtain 244.61 volt. Let us say in this problem you would have asked that torque angle or load angle delta. You can easily calculate it from there. You have the imaginary component, you have the real component. So delta would be nothing but tan inverse minus 17.32 divided by 244. So the benefit of
Sir,
this, yeah, please.
sir, in the power formula, it is given that root 3 V line to line voltage multiplied by IA cos theta.
Hmm.
Sir, but the real formula is should be root 3 voltage line voltage multiplied by line current.
Yes, you are correct. So this is a
But
star
sir,
connected here. So in a star, line current is equal to phase current, right? Here it would be line current. That's for sure. This is universal formula, which is root 3 VL IL cos phi. But in this problem, armature current is a star connected. So whether it is line, phase, doesn't matter in a star. In current, in voltage, we have to convert. Sure. Is it fine?
yes, sir.
Okay, thanks. So I was saying about this equation, this complex equation. So from this equation, this one equation only, you can find two variables. That is load angle as well as the magnitude. So only magnitude was asked. So magnitude we calculated. If load angle would have been asked, we would be able to calculate the load angle. So this problem is solved here only. 244.61 voltage by the answer, I guess. Yeah. So this why the answer. So any issue or any doubt in this problem? So this why the problem, if you can see it clearly. So we moved ahead with the basics of circuit and power flow equations. And after that, how we can connect all the things, that is very important. And in this problem, the major catch was losses where it is occurring, it was not mentioned. So that's why we directly jumped from the shaft load to input load. Otherwise, we would have stopped at developed level, or and we would have calculated EF from directly from there. In power equation, if you can see, there is two terms, EF, VT, delta, and theta. So that's the thing here. Uh, I want to derive it for developed power as well, this formula. If you can see, so what would I have done for S developed? So for S developed is happening at this side, EF angle minus delta and IA angle phi. Let us take lagging power factor. So developed is EF angle minus delta, or just started from basics, EF IA conjugate. So this is the developed apparent power. Again, you have to go like that. You have to break IA conjugate into two terms, VT minus EF. Just the change would be here, mod EF angle minus delta at the place of VT angle 0. It would be multiplied with IA angle minus phi. And you know the IA expression, EF is anyway there. So you can easily solve this problem. Based on power or reactance or current of synchronous motor or generator, it is very easy. For generator, the KVA would be EF, since supply is coming from the mechanical. So in alternator or three-phase generator, three-phase generator.
Sir, small doubt, sir.
Yeah, please.
Sir, load angle means theta is a small load. This
Sorry,
step,
can you repeat it?
load angle is equal to tan inverse into minus 17.32 by 244. Can explain, sir, in this step.
Okay. This term, right? So in excitation EMF in this equation, EF lag by load angle from terminal voltage, right?
Yes,
You
sir.
agree? Now, if I calculate EF, it would have some magnitude and some angle. And to calculate any angle, it is the real it was the real component here. Let me change the color.
Yes, sir. Sir, in this step also, by step also, k theta is equals to root over 244 square plus 17.32 square. In the step only explain, sir.
Okay, how I am jumping from this step to this step, you want to ask, right?
Yes, sir.
Okay. See, this was the VT, this was the IA axis, right? And if you break it into it will be broken into two components, 21.65 cos 126.86 plus J sine 126.86, right? Cos 126.86 would lead to some positive value or no, some negative value, okay? And what exactly it would lead? Let me calculate it. 26. So it would be minus zero point 0.6. So and plus J 0.8. If I will multiply 21.65 into minus zero point 0.6, it would be some negative value, and negative would become some positive, and it would be approx 13. So it would be added to 231. So it would become 244. Are you able to follow it, or should I explain in some clean paper? You got from where these two components are coming, since it was complex. If I will break into cosine and sine, so cosine would be real term, sine would be imaginary term, and this was already real. So real and real would get added. You are following? Who asked? Can you reply me? Okay, so
हम लोग आगे बढ़ते हैं सर, वो लगता है
okay,
आगे नेक्स्ट क्वेश्चन।
okay. So I hope I am able to explain you. If you have any doubt, you can again ask me. So this was the thing here. So I was talking about three-phase generator, and in generator, we give some mechanical power. Input is mechanical and output is electrical. Again, I think it is not visible.
Sir, you can select one of the default colors. I think it will be more visible.
Okay, this is fine. This color is fine.
Yes, sir.
Okay, thanks.
Sir, one question is,
Huh.
sir, in induction machines and DC machine, we are not concerned about the load angle in while using the KVL equation for the
Hmm.
circuit.
Hmm.
In a
Yes.
synchronous machine, we always concern the load delta
Delta.
load.
Mhm.
So why this?
So a synchronous machine is not self-starting machine, and it is AC machine. So first, let me compare it with induction machine. So induction machine is self-starting machine, and here we can control on the basis of slip. But synchronous machine has the control parameter of delta, and it has always issue with stability. If you don't maintain delta, it can go in unstable region, you can say. And in DC machine, since it is DC, so there would be no relation of any phases or any angles. So DC machine is the separate machine, but induction machine is self-starting, and here we can control from a stator, because what happens in induction machine? Let's take a squirrel cage induction machine because that is by default and popular induction machine. It it's a stator supply the flux as well as uh, power. Okay, and it has the induction. It has the induction property. It's its current or power it get induced like transformer. So we can control everything from the stator side itself. We don't need to take care of any other parameters from the rotor, because rotor is it is maintained from the stator side only, since a stator is controlling both things. But in synchronous machine, it has a stator winding.
Sir, some noise is coming out, sir. Can you
Okay,
please tell him?
the person who has asked the problem, can you mute yourself, please? If you have any doubts, you can ask and you can unmute yourself.
Yes, sir. Now I'm muting you.
Yeah, thanks. And rotor. A stator has the armature or this powers. It provides the power.
Sir,
Yes.
stator అంటే ఏంటి సార్? Stator can explain, sir.
This person. Yeah.
Yes.
Yeah. So synchronous machine has a stator or armature that is placed on a stator side, and is field is provided on the rotor side. Rotor side, sorry. So on rotor, this is able to maintain the flux whatever is required to run the machine at rated or even in field weakening. And a stator, this is the thing which is providing the electrical loading or power. In first session, I guess I had discussed about electric loading and magnetic loading. So if any machine that try to run, they should maintain two criteria. They should maintain the rated magnetic loading and electric loading. And electric loading is known as power loading, or you can say power supply parameter. Or magnetic loading, you can see as a flux supplier. So in induction machine also you might be able to heard like magnetizing component. So that magnetizing component is like 40% of no load or of a stator parameter. So that magnetizing component is coming from a stator side. While in synchronous machine, that magnetizing component is coming from the this rotor field. So this field is independent. And if this field would have some angle, right? Let's say synchronous machine, we give the balance supply, and its a stator RMF is moving at ns. And if rotor is not rotating with respect to this stator RMF, then there would not be any coupling and this machine would fail to start. So that's why we try to maintain the load angle between a stator and a rotor, or in circuital term or parametric term, Vt and Ef. So we always try to maintain this angle below 90 degree, that you will study detailed in power system stability chapter. So this was the basics behind them. So that's why we do not care load angle in induction machine. So is that answer is clear, or you want some more clarification?
Yes, sir. Clear, sir. But
Okay.
sir, in the synchronous machine is related to also the power system. So,
Hmm.
sir, it is necessary to read from the like the Fitzgerald book.
Which book?
Sir, electrical machinery A. Fitzgerald, yes,
Acha,
something.
Fitzgerald. Okay. You can refer any book, but you just have to understand what happens with the variation of acceleration and deceleration with delta. So what is the effect of this delta? So that chapter, that transient or that power system stability is everything about that delta. So you that is more, or you can say that deep concept about this load angle. But in machine, there is no relation with that. Here, you just need to know that what is delta, how it is lagging, how it is leading, and what is the angle basically. So if you say to make any torque, let's say this is the field component and this is the armature component. To produce torque in any machine, okay, torque is
Yes, sir.
directly proportional to FF and FA and the sign of this. So if both are orthogonal, we are trying with the help of lip rings or brushes to maintain both the components orthogonal so that we can achieve maximum torque, right? So torque, and this is the sign of FA and FF. If angle between FA and FF is 90 degree, it would be maximum torque. It would give you maximum torques. And generally from power equation also, you can see EV by XS if armature is ignored sine delta. If delta is 90 degree, you have maximum power corresponding to the torque would be maximum. So, I will explain this phasor now since I have mentioned it. There would be one resultant. Okay, this MMF is due to armature, this MMF is due to field. So one resultant would be, and this is generally delta, right? Corresponding to that one, let me, okay, so orthogonal to this vector, EF would be generated, okay? And orthogonal to this FF corresponding to maintain that amount of field, VT would be generated. So this angle is similar to this. So generally, you see torque is equal to FF, F resultant sine between them, FA and F resultant. Now, F resultant would have some component that would FF, or let us say in some hypothesis or in imaginary world, there is some machine which is providing field from a stator as well. It has field winding as well as it is providing field from a stator. So that term would be added to this axis. Actually, I went in some advance, but no issue. I hope you would be able to follow here. What happens in advanced electrical machines, some components, this axis is known as D axis and this axis is known as Q axis. So the, on D axis, F resultant across D axis would be FF plus F resultant cos delta, and F Q axis would be F resultant sin delta. And after combining these both terms, if you combine this both terms, you will get two component. One would be the electromagnetic component and one would be the reluctance component. And the reluctance component would lead these two terms, cos delta, sin delta. So that's why in some machines, some advanced reluctance machines, this is the fundamental from where reluctance component generates. And this would lead to you nothing but the electromagnetic torque. So let me write it. F resultant sin delta plus F resultant square sin delta cos delta. If you guys are familiar with reluctance component, it is fine. Otherwise, it is also fine. So you can further write it as F resultant square by 2 sine 2 delta. So this is the reluctance component. I guess once in 2018, one problem was framed based on reluctance component. So I guess it is in the syllabus. And it is electromagnetic. Electromagnetic due to electromagnetic due to the field, whichever field you are applying or the flux component is there in the machine. That's why electromagnetic component would be generated. But this reluctance doesn't have to take anything from the field. It is generally the difference between the reluctance path. Generally, in it is found generally in salient pole type of machines. So in salient pole, let us say one alternate one. This is a stator. This is a stator surface. However, it would be in the tooth shape, but let us say it is cylindrical. So this is the minimum reluctance path. Minimum reluctance path. And a minimum reluctance path is known as d-axis. And this is the maximum reluctance path. The air gap is huge. And due to this gap, the reluctance torque generates. So why due to this gap reluctance torque generates? Because if a stator MMF is rotating at synchronous speed, and rotor surface would always try to catch towards this origin, least reluctance path. So that is the property of reluctance, right? The machine or any path or any steel or any core that would try to attain the minimum reluctance path. So that's the fundamental property of reluctance machine. So I hope you would have grasped it. So any doubt?
Sir, for the purpose of the real power, the power should be flow from higher torque angle to lower torque angle,
Yeah,
stator and the field winding.
yeah.
But how the reactive power will flow? In which direction?
The total power, no, reactive power has some concept of lagging power and leading power. So from delta 1 and delta 2. So let's say this machine is overexcited, and if overexcited, then it would have higher EF. Okay, higher EF delta 1, and this is EF 2 delta 2. So this all concept would come if I derive the reactive power equation from that developed or that apparent power. So this was the developed power. So here, if I will break in two components, then I will or anybody will be able to say that the flow of reactive power is from this to this. So generally, what happens in machine, I will derive that equation. Do not worry about that. So generally in machines, if machine is overexcited, so it would always try to supply back to the grid or to the load. Or if it is underexcited, it will always try to take from the supply. So there is two conditions. So let me derive the Q for developed. That was EF angle minus delta IA conjugate VT angle 0 minus EF angle EF angle minus delta divided by ZS. So this is the apparent power in machine or apparent developed power in motor. So after that, EF angle minus delta. I will try to take the conjugate right here. VT angle 0 minus EF angle delta divided by ZS angle minus theta. I will multiply it here. EF VT angle minus delta minus EF square. Sorry, and delta plus theta. Delta, this plus and minus would be cancelled, so theta would be there. Okay. So I can find the reactive power developed EF VT by ZS sine theta minus delta minus EF square by ZS sine theta. So this is the formula of developed reactive power. You do not need to remember anything. You can write just like it is. Okay. Now, when any or inductor, let's say example of inductor, if let's say it is overcharged, so in terms of machine, if it is overexcited, it will try to provide the power in terms of reactive power. So generally what inductor provides, it provides lagging power because it has excessive of lagging power. Okay, so if this Q developed is zero, is higher than zero or positive, okay, so if Q developed is greater than zero, it will provide or it will supply lagging reactive power. If it is less than zero, it will absorb same lagging reactive power. In other terms, you can also say if Q developed is higher than zero, it will absorb leading power, leading reactive power. So any one nomenclature, if you will keep in mind, then you would be able to say. So now, when this machine would be in, overexcited, when this machine would be able to provide power, whenever this term is greater than zero, and when this term would be greater than zero, so you have to do some mathematical analysis here, and let's say some condition would come out Vt sine theta minus delta. Let us equate to greater than equal to 0. So Zx would be cancelled out. So Vt sine theta minus delta would be greater than Ef sine theta. Okay. So when this condition is followed, then your machine would be in overexcited, and then your machine would be able to supply the power. So that is the basic funda behind it. You cannot directly see and say that from higher delta to lower delta, it would be supplying, lagging, or leading reactive power. So are you able to get this concept?
Yes, sir. Now clear, sir.
Yeah, thanks a lot. So any doubt in this topic? I guess I have covered almost things. I will move to another topic or one more topic related to parallel connection of this motors or synchronous condensers. There you will be able to understand more what happens when any motor acts as synchronous condenser. So what is generally a synchronous condenser? I will discuss that topic. So this is the problem based on parallel connection of synchronous machines. It appeared in GATE 2017 in session 1 for 2 marks. Okay, so please read the problem and we will proceed. Yeah. So two parallel connected three-phase star connected synchronous machines A and B are operating as synchronous condensers. So synchronous condensers, whenever you see, it will be overexcited motors. Overexcited synchronous motors. What does it mean? It means it has more reactive power and now it can supply some reactive power either to load or to grid or to any such kind of absorber. So that's what these both machines are connecting in parallel and they both are supplying reactive power to the grid. It is given here that grid is maintained at 50 MVAR, 11 kV. So this
Sir,
11,
will it supply leading reactive power or lagging reactive power, sir?
I just now explained, if any machine in overexcited, it will always supply lagging power. Okay, it will have, or in other words, you can say, uh, let's say inductor. It will act similar like inductor. So what does inductor do in buck converter or any? If it was charged, now it will be discharged. So it will provide
Sir, I
lagging.
think,
Yeah, what do you
sir, I
think?
think synchronous condenser will provide leading reactive power, sir, to compensate lagging reactive power in the grid or something load
Okay. Okay, so then I will go
like
back
that.
and check this if you say so. I may be wrong. It's not a big deal, but up
Yes,
to,
sir. Synchronous condenser is a overexcited synchronous motor under a load, no load conditions.
yeah, that's overexcited synchronous motor that I am saying. But the issue is here whether it supplies leading power or lagging power, right?
Yes, sir. I knew like it will provide only leading reactive power for the
Okay,
lagging load, sir, like
okay,
that, sir.
no issue. We can just right away we can search on Google
Yes, sir. Take
overexcited
that one, sir.
synchronous. Uh, no, I just searched on Google and it is saying an overexcited synchronous motor draws leading current. Means just the opposite. You are also correct, but just the opposite. I told you there is some confusion. If it supply lagging power, it can absorb leading power. So you might be remembering from that terminology. So there are two terminology. Just what I explained here.
Yes, sir.
Uh, So absorbing leading power is same as not delivering, supplying lagging power. And this I am talking in terms of reactive power. Okay. So
Yes,
you
sir.
should not be confused regarding this. This is very confusing. Till date, I am being confused. Okay. So nothing new. But in general, how I remember every time these confusing things. So if any machine is overexcited means it has more flux or it can supply more reactive power. Then it will supply lagging power because the grid in need of lagging power. Then only if it absorbs lagging power, then only it can supply to other machines because all machines need lagging reactive power, right? So that's why one machine is overexcited. It is supplying lagging reactive power to grid. The grid further it can supply the lagging power, or the bus, from the bus it will go to the other under excited motor. So like this kind of terminology you can fix it in your mind. So
Yes, sir. Got it, sir.
thanks. So again, coming back to the problem here. So this 11 kV grid was there and 50 MVAR. Uh, they both are supplying equal current. So let's say first I will draw one. Let's say it has negligible armature. Generally, what we assume in UG courses that armature resistance is negligible. Now, this is the bus here. Let's say this is the bus. This is means 11 kV grid and 500 MVAR, I guess. 500 MVAR. This is the rating of the grid. Now, this alternator 1 or motor 1 or condenser 1, let me write it as machine 1. It is more generalized, and machine 2. Now, the terminal voltages are same. You can write or denote in circuital form. Fine. Terminal voltage is same, 11 kV. Currents are also same. IA1, IA2. Okay. Currents are same, but something is different. That is saying that synchronous reactances of machines are different. 1 ohm, J1 ohm, and J3 ohm. So these reactances are different. Okay, now we have to find the ratio of, let me show you the problem again. Synchronous reactances are given here. Now we have to find, and one more important thing, we do not have to worry about any saturation since magnetic circuit is linear. Now, the ratio of excitation current of machine A to machine B, that's what we had to calculate for 2 marks. So I would say IF A1 divided by IF A or B. IFA to IFB we had to calculate. In synchronous machine, we all know field is supplied by the rotor. The field is wound on the rotor. So excitation EMF is related to the field current. So here, if I will write it as EFA divided by EFB, it would not be wrong, right? Any doubt in this step? In DC machines also, the excitation or the armature MMF is proportional to field current, right? EF is equal to K phi omega, if I remember correctly. So like that. So excitation EMF and EF would be in same ratio. Why? Because there is no any saturation. That's why this condition was given here. Magnetic circuit is linear. Means you can supply the field current, the excitation EMF would follow the same. The excitation EMF would follow the same. In general, all whichever machine works, there it is not. There, if you increase this, it will get saturated. So it will excitation EMF would not increase in the ratio of field current. So, and that was the catch. So one catch we found. Another catch we have to calculate. That we have to calculate now EFA, EFB. If we can calculate anyhow EFA and EFB, our job is done. Now, this machine has, I will write the KVL equation of machine A. EFA would be VT. VT is same, terminal voltage same, and both are in parallel, so voltage would be same. Terminal voltage would be same. Minus J IA Xs. resistance is ignored, right? IA1, XS1. This is equation 1. In equation 2, I will again write VT. These are AC components, so we should include phases. This 2. Now, XS1 is given, XS1 is given, XS2 is given, VT is given. IA1 and IA2 are not given, but we are mentioned with both are equal. Now, we have to calculate IL. We can calculate IL because these two parameters are given. So any power, apparent power, real power, reactive power is given. Our first attempt should be related to calculation of current, armature current. So I will calculate IA, that would be Q divided by 3 VL IL cos phi. Okay. Oh, sorry, sine phi. How we can calculate? We will need phi, and there are no any information regarding this angle.
Some formula is not understood. Why IA is equal to Q of my root 3 VL IL sin phi.
Okay.
Why IL is here? We have to calculate the IA.
IA and IL are same. Whatever. Okay, let me more clarify it. IL is equal to IA1 plus IA2, right? The current supplied from machine 1 and machine 2. But this grid would have again some current, and this grid will have some power. S equal to root 3 VL IL. Since this grid is operating at 50 MVAR, means it is only taking reactive power. So we will take Q root 3 VL IL sin phi. I am writing only this formula here. So do you have any issue with that now?
Sir, my question is here is IA is equal to Q of my root 3 VL IL sin phi. So now that means that Q is equal to root 3 IA multiplied by VL IL sin phi, na? Then reactive power is proportional to IL multiplied by IA.
Okay.
Sir, he is asking about a denominator, sir. It is a root 3 VL sin.
Yes,
Okay,
sir. In the
okay.
denominator, you have
Thanks,
repeated the current term.
thanks. Yeah. Sorry, I mistakenly written that. Thanks a lot.
So,
Sir, next lesson is started.
Sorry, next class is just started.
Yes.
Okay, so actually I wanted to extend this class to 1.5 to 2 hours. So is everybody else is about to go, or we can discuss in later or next week as well.
sir, next session.
Okay, so you all have to attend the next session, right?
Yes, sir.
Okay, fine. Okay, thanks. So I will stop the session here. Thanks a lot for joining. So some
Thank you, sir.
comments are also there. Then what will be its speed? I think some doubts are there. I will copy it so I can add this in next session. Okay, thanks. You guys can join the session.
Sir, thank you, sir. Thank you for joining.
Thank you. Thanks a lot.
Thank you, sir.
Thank you.
Thank you, sir.
Thanks.